Alex.
Hello. So my name is Carlotta, also from the 3D Native team. So our next presentation is with GEFERTEC and Siemens. It's actually going to be a co-presentation on the holistic development of use cases for 3D metal printing technology. So we'll be joined by Alexander Riemann, Head of Applications at GEFERTEC, and Ollie Geisen, Head of Engineering Services for Additive Manufacturing at Siemens. Welcome to you both. So Ollie has been with Siemens Energy since 2012 with a focus on large gas turbines. He has been a manufacturing engineer on gas turbine combustion engines programs and project manager on gas turbine prototype programs. So his career in additive manufacturing began in 2015, where he has held roles as program manager for a host of public research programs and as digitization lead. And he's currently head of engineering services for additive manufacturing, focusing on AM design and engineering and AM training and consulting. So Alexander has, from 2003 to 2008, has worked as a construction mechanic for Bombardier Transportation, where he focused on the welding-related production of railway vehicles, followed by the fabrication of bridges until 2009. And while studying automotive engineering in Dresden, he also worked for BMW Group as an intern in the prototyping department. So Alexander has been with GEFERTEC since 2015, and he started in the field of process development and is now working as the head of 3D metal printing of the 3D Metal Printing Application Center. So welcome to you both. I will let you move on with the presentation, and I invite everyone who's watching to send in their questions in the Q&A so that we can allocate a few minutes to answer your questions. Thank you.
All right. Yeah, I'm going to start. My name is Alex. Thanks for the introduction, and thanks a lot for joining the event today. With me, yeah, we already know it's my co-referent, Ole Geisen, and I will just start with a little overview about our additive manufacturing landscape, so where we're coming from. So basically what we see in the industry right now when it comes to metal additive manufacturing, we have different processes such as laser or electron beam as a heat source, so beam-based. Coming from beam, you use mainly as a feedstock wire or powder, and one main technology being available for metal additive is laser powder bed fusion. We as GEFERTEC, we went a little bit a different way. We kind of worked on the right-hand side here. So we have an arc-based technology, and more precisely gas metal arc welding, and we called the whole thing 3DMP. What means 3DMP? For us, 3DMP is 3D metal printing. So we combine our CNC machines with the wire arc additive process, and also with our own CAM software, and this package together enables you to really print parts. On the next slide, I'd like to talk about a couple of applications we have run through the last couple of years, and our kind of main industries or applications we could find so far. One of them being tool manufacturing, so such as repairs or even building up a full tool. The main advantage we see here is that you can use different materials to build up one part. So we use, as I said, a wire as feedstock, so it's easy to change, and you can use two or more different materials within one part. The advantage here is that you actually be able, in this case, to have a pretty ductile body, and then maybe combine this with a really hard surface, which you need for such applications. So you really have the properties in the part where you need them, and you only apply the material where you actually need them. This also reduces production cost, or lead time. And of course, you don't need a machine, a full big hard chunk of metal. You just need to actually machine the hard material where you need it. Another area of application we are working in is those propellers or impellers you can see here. So propellers being more used obviously in maritime applications. Usually the production method is having a casting or full machining of a block. Here the materials being copper-based alloys, or high alloyed stainless steels such as duplex steels. Main advantage here again is lead time, so you don't need to create a form or anything to build up a part. So engineering cycles and development cycles will be reduced dramatically, and also with this you really save a lot of money in building up forms and building or creating those parts. Below this, we also see impellers. So of course we are looking into a little bit bigger parts. We have a high deposition rate process. So bigger impellers used in oil and gas industry are pretty good to actually produce with our technology. So here again, forging long lead times is a problem, which really increases the price or the cost for such a part. And this with our technology, it's possible to really reduce that and build up parts with, in this case, high alloyed stainless steels, for example, such as 74 pH or 55 pH. So build them up quick and reduce dramatically reduce machining. We are also working and looking into aviation and space. Main material here obviously being titanium. So you see brackets here. We have done many of different geometries like this. They are all pretty much the same, look pretty similar. And so again here we are able to build big parts, and you save a lot of machinings, which would be one of the standard process. With titanium, it's very complicated because recycling of the chips is pretty expensive. The material is pretty expensive, so parts will be expensive too. Here again is a possibility to reduce cost and to build up lightweight, high strength structures. And the last use case I'm like to talk about here is gas and steam turbines. So you can see here those blades. We are working in these applications as well, because here again machining, forgings are standard production methods, and for those blades which can be different sizes, very huge actually, which fit pretty well in our machines, it's possible to actually substitute the manufacturing method to 3D-MP. Here we are working also on high stainless steel or high alloyed stainless steels, and as well on nickel-based alloys, for example. Mainly with 3D-MP, we are looking for, or basically for the implementation of such a technology, we are looking for simple or medium complexity parts with pretty, more or less expensive materials and or high machining. So with this, I'd like to hand over to Ole with the next slide.
Thank you, Alex. Can you guys hear me okay?
Yes.
Good. So let's start use cases for additive in general at Siemens Energy. One thing to show here that I wanted to start with is one of our main products, one of our main drivers for additive today, and somehow the reason why we've been early adapters of additive. It's the gas turbine. You see it here. It's a product that is competing in a market that's slowing down a little bit. So you gotta got to really push new technologies if you want to survive in that market. It's quite clear. So you have to have higher combustion temperatures, better fuel flexibility, stuff like this that really keep requiring better technologies or better solutions. And you also have supply chain issues, I would call it challenges, that will also drive you towards new technologies, right? Faster repairs, faster time to market, spare part availability. All of these things were the main reasons why we went into additive years ago in the first place. The use cases, the main use cases for us internally, you see here on the right-hand side, starting still with rapid prototyping and, still important use case. This means you use additive to validate a new design. You get real testing data, you confirm that your design was good, your idea was good, and then you go back into conventional manufacturing. Usually this is if you have, a large serial production and cast might be more economic. These are still cases where we have AM today, fast technology validation that makes a lot of sense for us. Second one is rapid repair. That's usually taking a component that has been in service, cutting off a piece that somehow has been damaged, and then printing on top, right? So this is something that has been done or has been developed years ago and has been, kind of optimized over the years. Spare parts on demand, very important topic. So for engines that are 30 years old and where we still need to provide spare parts, it makes a lot of sense to check additive. This could add a lot of value. Technology substitution, difficult one. Usually this is to reduce cost. So sometimes you can use a certain additive technology, just like 3DMP, for example, and be more economic than what you had before. These cases, you don't find them that many or that often, but they exist, right? And it makes sense to look for those. And then last but not least, design for AM components, where you completely change the entire design setup to get the best performance out of your part. Important point is we've been doing this all for the gas turbines and for other Siemens Energy products, but lately we've been pushing quite hard to bring our services in different industries, right? We've been covering oil and gas, aerospace, and so on. So a lot of the things that we developed in-house now serve as basis for services we also provide externally. And the key somehow is that all of these new technologies, all of these new applications, they always require a very good qualification. And that will be the next slide, because now if you have Alex, can you? Yeah, thanks. No, next slide. Yeah, that one. Thanks. So whenever you start digging into a new technology, and here we see 3DMP, we see the WAM, wire arc technology, you have to make sure that whatever you're doing is good enough to meet obviously your requirements, but also make sure it's repeatable, that you can ramp up a serial production using a new technology. And that's something that we have really mastered over the years. Defining the right process parameters, you see it here, it's just an example on the left-hand side, finding the most suitable process parameter, and then going into a full characterization and qualification of this process parameter. Meaning I have to understand what my fatigue properties are, what my creep properties are, and so on. So once I know how I want to build up a part, I have to go through an entire program, making sure that at the end I have a fully released process that is okay to use for customer parts. Because remember, and Alex has shown it, these are critical components sometimes, right? A blade, you cannot just print a blade and hope it's gonna hold in the engine. All this stuff needs to be done the right way, and this is where we see a lot of potential. Also working with GEFERTEC directly to make sure we have a very robust process that is usable for customer parts. Alex.
Okay. Yeah, and so, well, so having done all this qualification processes, and all this talked about having stable process parameters and things like that, now it becomes really necessary to keep track on these parameters and make sure that they stay in a range and they will be always stable throughout the whole printing process, or even throughout the production of many parts. So therefore, we have developed our own hardware and software components. For here on the right-hand side, you see our sensor head, quality monitoring features, meaning with the hardware or the sensor head, we are actually using a camera system, looking at the here on the bottom, looking at the weld seam, looking at the melt pool, to really see if something goes wrong or something is different compared to the standard we have defined prior. We are also looking at all the main parameters, and this is something which is, I think, pretty easy to do, or let's say more easy to do compared to other processes. We have let's say a welding process which is all based on the wire feed rate and on the wire actually creating the arc. And through that, we are melting the material. So if we understand the main parameters such as voltage, current, wire feed rate, and gas flow, and things like that, and if we monitor them, we can make sure that we stay in a range and see if something goes wrong, if anything falls out of range, if you need to change consumables or something like that. So these tools, hardware and software, also provide you a solution to actually do the full documentation for these critical components. So you can make sure that you can, throughout the full build-up process, you have kind of an in situ control, in situ monitoring, which saves a lot of money in the post-processing. So you can actually reduce testing, like final testing, destructive testing, for example, or also non-destructive testing if the parameters are right. And with this, you can even accelerate the whole production process and the qualification process. Another tool we are using to actually visualize what's happening in the machine is called the 3DMP Cockpit. This is kind of a software tool which enables you to use your mobile device, your smartphone, your laptop, whatever, to actually see your machines running, to get an idea of what is happening, how far you are with the build-up process, for example, or even get statistical evaluations about the whole build-up job or the batch production. So all this together, this is more or less software we are offering to our customers to make sure you get the best parts and the best quality control for the production of the parts. Here, I'd like to talk also a little bit, not only software, also about hardware. So mainly we're basically a machine manufacturer. So obviously we also produce and have developed our own machine systems. You can see here the two machines, basically the two systems we are offering. It's the 405 in this case here on the top, and the 605 on the bottom. Actually, it's two types, both available as 5 and 3-axis version. So it really here again depends on the part complexity. I said we are really focusing on medium to low complexity parts. So if you want to be a little bit more complex, maybe having an impeller or something like this, then you can use a 5-axis system to actually manipulate the part underneath the torch. Or if you're really looking for bigger parts, then the 3-axis version is probably the way to go. To have heavy parts up to 3 cubic meters in size, or up to 3 tons in weight. So you can really have pretty heavy parts, pretty big parts for even repairs or things like that. we are using those systems, by ourselves as well in our 3DMP application center. For us, in the application center, we want to provide the customer the full experience of this technology, meaning we're going through the whole process chain, talking about business cases, helping the customer to develop their business case or use cases for this technology. So we are kind of starting on the CAD model, really really looking at the design of the parts, do iterations, optimizations of the designs. Also together, Siemens, for example, is a good partner for doing this in a more complex way. But basically, with this optimized CAD model, we go through our CAM software, do all the slicing, and prepare the part for the actual printing process. We have to create an optimized printing parameters. So depending on the materials the customer need, we have to optimize and create and develop process parameters which enable us to have a stable process and good quality parts. And with this, of course, we go through the printing, we look at the QM tools, we do the full documentation and the post-processing to really show the customer what is possible. Apart from that, we are also offering all the necessary services with the team and with the machines we have here in Berlin. Okay, Olga, I hand over the presentation to you again.
I'm sorry, Ole, just so you know, we can't hear you. If you could turn on your mic, that would be great. Thank you.
Thanks for reminding me. Okay, we lost 20 seconds here. But very quickly, yes, Alex mentioned these use cases where you want to actually improve your design a little bit. You want to dig into what AM really can do for you, what 3DMP can do for you. And this is when we can add some value, right? This is when we can, with our background, start working on solutions. Now, next slide, Alex, it's just an example of a topology optimization. If it shows up, yeah, that one. And obviously, we've seen many topology optimizations, many of these pretty bionic shapes. The one thing to really keep in mind is if you go through a workflow like this, you have an initial design, maybe a milled part, you get into a couple of new topologies, so crazy shapes that might be lightweight. You do your FEA, you do it for the static load, you do it for dynamic load, you see it here. The very crucial point is that none of this really makes a lot of sense if you do not understand the materials. You have to go through a characterization first to understand how the material behaves, right? And how this will affect, for example, the lifing. If you have certain surface characteristics, you need to respect those when you do your lifing, right? So just taking properties for a chemistry that's widely available, let's say Inconel 625, you can take that, but it will not allow you to make a very precise simulation of what you are looking at. You have to characterize your additive.
Ollie, I'm just gonna jump into the Q&A, if that's okay. The presentation was really nice, but we have a few minutes and I think we can answer a few questions, and then any that haven't been answered, we will invite you to join the tables. So the first one is, what are the main risks of producing turbine blades in additive manufacturing compared to CNC machining?
I can try to answer this. So a blade cannot fail. It's a rotating component, so it's a highly critical component. So you have to make sure that you have no defects in such a part. It's the biggest damage you can have in a turbine is a blade ripping off, stage one, and then taking off all the other blades and vanes coming after. So you have to have very good non-destructive testing to make sure your part is really safe to put into the engine.
Okay, and does GEFERTEC work with customer when installing and qualifying the machine and aid in the development of standard operating procedures?
I mean, this is one of our main interests, to really understand what is necessary to implement such a technology within the customer side, or actually provide to get parts on customer's side. Yeah.
And to ensure the repeatability of AM, especially about the mechanical properties, what kind of NDEs do you think is effective for AM materials?
Oh, yeah. Maybe I try, Ola, and then maybe you can add some comments. So mainly, this is also what we are talking about prior. So it is really about making sure that the parameter set you have developed and proven that it is working prior is being pretty stable while the printing process. So the combination of creating a stable parameter set and then having quality management tools such as the sensor head I've mentioned, this will be actually making sure that parameters stay the same, and then also the quality of the part is always the same. Of course, there's other points, so we have to also look into the wire feedstock, for example, or gas or things like that. But this is all also covered with standards. As we are working on a basically standard welding process, it's pretty good because everything is already pretty much standardized for automated welding applications. So we kind of build everything up also on that.
Okay, great. And just one last one. What materials provide 56 HRC for tools and to achieve corrosion-resistant parts? Is it post-processing of material properties?
I'm not sure if I understood the question right, but I think for, of course, you need post-processing for certain parts, especially machining and heat treating sometimes. But this is more about stress relieving and things like that. Corrosion resistance is usually been given through the material you choose. Does this answer the question?
Hi guys, I think it does. It seems like Carlotta is having some technical problems. For any other questions our audience might have, Alex, Ole, and I'm sure you would be more than happy to speak with them during the networking sessions. Perfect. Well, thank you so much, both of you guys, for your time. Hope you enjoy the rest of DAM, and we'll see you all in a bit.
Cheers, bye-bye.
Cheers, thank you.